Hi there. After finishing our first hour, now we are starting our second hour with Mr. Elio to talk about or to continue talking about the PV solar systems, the maintenance, and the testing. Now, Mr. Elio, the floor is yours. You can start your presentation. Yeah.
Okay. So we got already some questions, so I will just ask a few of them. Some people ask about the voltage again with a 420. So 420 is, as we know, already way too high. So go to a decent voltage which you're used to have, like 400 volt. So that means from 422 or 417, whatever you may have, go back to 400 volt. Then some people ask about the apps I'm using. So the apps is unfortunately in every country different, but I just give you some names. Some is they work in some countries, and in some countries they don't. So one of the ones I showed, it's my solar panel. You have Scan the Sun. You will have Solar Might, which works mostly in Asia. Solar CT, that's also in Asia. Solar and PV. You have Solar Tilt. So it's self-explanatory. Solar Tilt will be the tilt you encounter, and you can optimize or should optimize, or you can see. Then there's another one, PV Solar Forecast. You have Solar Home that works also in hybrid mode, for example, with batteries and with the line conditioners. You have Sunshine, you have something like Sunrise, Sunset, or PV Optimizer. So once you have one of these apps, the other one will pop up on its own. So just check your iPhone or your Android apps and have a look what they give you, and then it's forwarding by itself, or ask me in an email or as a follow-up again. But those are the mostly I use during these systems. What we see now is the system factors, where you had the different voltage levels depending on negative grounding, ungrounded systems, or ground referencing systems. That was for thin film modules, for thin film inverters, solar, First Solar, or Next Power was also one. There was a lot of different ones, and of course some module suppliers, or now PID issues, which we see. You have to either earth the negative or the positive. In America, by law, you're supposed to earth one of the poles. This is not like happening in Europe. They do it because of PID, but normally they are actually not earthed at all. But like I said, it's interesting to see the different scenarios also with hybrid inverters, whether they are DC charging or AC charging, and you can see the different fluctuations of the AC grid, and then you have the different transients and different radio waves. That's tiny, but hopefully you can see those are the power produced in a 10 kilowatt system. You see the currents in different days and time frames. You can see the voltage, which is here 350 to 347. So like I said, most of the time these inverters have a specific nice to have MPPT, and they will try to go back to these values. Also, you can see the insulation resistance. That's the fourth column. When you get the slides, you can see it better. But those ones, for example, are 618, 665 kilo ohm, 560. So they are quite low. And those are prone, if you see that, if you go for central grid inverters, it's even worse. Most of the time they are between 150 and 250 kilo ohm. There should be 1 mega ohm, but depending on your earthing and sub-earthing and bonding and cables you're using, you have these values. Now, when it gets wet, or as I said, morning dew or nighttime, you have these problems, that they are 10 times higher in leakage, and these leakage will switch off the inverters, and you have a lot of phantom ISO faults, which you should not have. The leakage of each individual inverter, in this case, for example, you can see it's 43 milliamps on the bottom column, up to 60 milliamps. And each individual inverter manufacturer normally gives you also in these instructions the maximum amount of current they have. By law in Europe or in Germany, especially with the VDE and similar inspection commissioning criteria, higher than 30 milliamps, you would need a second earthing at the chassis. So it normally is not allowed to run the system only with a wire inside the cabinet. When you exceed 30 milliamps, you are normally supposed to earth it twice. So, and the second is the chassis grounding, and you will see the measurements I'm taking there. It's quite interesting. That shows now Tigo or SolarEdge or some Huawei, some optimizers you're using. So that's 275 watt Canadian modules, for example. They are shaded. So depending if they are shaded on the bottom, when it's vertical or horizontally, they will align. So in a inverter or multi-string inverter, this will be mostly 0 or a little bit energy. Here you can see instead of 180 watt, you optimize to 22, 7 or 21 watt, depending on the soiling or depending on the shading factor. So you get something out of it, but it's sometimes marginal, sometimes not worth it, or sometimes also depending on the amount of modules you're using. So overall, those systems work quite well, but sometimes in some appliances it's questionable. That's, for example, like I told to you in the UK, you use at the tables like a 16 millimeter copper cable from dish to dish. So from array to array to the monitoring, where you have mostly DC surge arresters, and then you have the inverter or the medium voltage, just to show you, or the interconnection of these earth bars. In UK, like I said, most of the time it's thermo welded with earth rods at the corners, and in Germany most of these stations are on a concrete base or have an earthing ring around it. That was an interesting installation in Romania, 50 megawatt. I checked the system, so you can see the inverter. Those were units with 50 kilowatt. You can see inverter 1, 2, 3, and 4 on the right-hand corner, 700 milliamps, 1200, 3790, and 4450 milliamps. So that's the leakage you can measure on the earthing schedule. And funny enough, this system was not earthed at all. You can see the red wires. These are my measuring leads, because that's the first thing I check. And in between those wire leads, you can see from 0.7 to 4.4 amps stray currents. So those inverters are master-slave. The master-slave function did not work. So what happened was that one of these inverters out of a timer-based string will be the main or the master, and then the more system comes online, the more slave will switch on. This was totally switched off, so the whole system was running during morning and nighttime, very insufficient. So the earthing was actually enough to get it back to master slave. Those are the blind spots, which we always say. That's a system in America, the Bakersfield fire. They found out that there was a faulted conductor, and they use, for example, 5 amp fuses, as a precaution from the negative or positive towards the earth. And there was 3 amps running on a 5 amp fuse. That means it is not taking off the fuse, so it will stay online. And so it was not enough to clear the fuse, and it started a fire at the modules from these string sub-arrays. So it is quite dangerous when you earth. I mean, these systems would not be done like that in Germany, and at that time, that's also some years ago, we also did not have so many problematic issues with that, because like I said, we don't earth one string. So we have 2 floating strings, plus and minus, and it's also easier to measure the startup voltage. Once, like here, you perfectly ground one pole, you can have these effects. So some pictures. That's what I said to you in the beginning. That's also happened in UAE in some days, that you have these condensing water droplets on the top or even on the bottom, so you cannot see it perfectly. But either way, that's enough with 45 milliamps or 600 to 800 kilo ohm to actually have these phantom isophores. So during that time, when you have the condensing water on top or bottom of the modules, you will encounter that the inverters will stop producing or show isofaults or show some numbers depending on the manufacturers. And it's this phenomena. It has got nothing to do with the modules, got nothing to do with the inverter, and also got nothing to do with the cables. So all in all, exceeding 50 square meters of a module surface, in adding a corrugated roof, which is like a capacitor, and different earth scenarios. So you have the modules, you have the roof, you have the soil, you have the AC inverter, sometimes 100, 200 meters away, and you have the transformer. If they are not interlinked to each other, you will face these troubleshooting problems that the system starts and stops on its own. That's another picture of these systems. We also encountered these problems with the bricks, with the floating device. Also later on, they installed some railings, and that caused, of course, a lot of problems with the shading and under performance of 10%. So even though the shading looks very small and tiny, that's already 17 to 30% of the module's performance, because it's affecting several substrings. If you install systems, I was in Pakistan and in some other desert areas. So they had an interesting solution in China, where they use these type of greening to get rid of the haze. So in actual fact, this is preventing. They also then make a greening of these spots. So the soil erosion is much less, the wind is less, and those modules are less in comparison. That's the Siemens inverter, like I showed you. So what the problem was at that time, that these people who are doing the checkups, they're checking their medium voltage side, and when you check the medium voltage side, you check like you check transformers only. I mean, that's at least what the Germans did. So that means 15 minutes intervals. So of course you never will pick up anything of errors, because the buffer of 15 minutes is just way too far. So I had to put the intervals down to 1 second. Took me quite some time to convince those people to do that, because I told them also, it's not on your problem, and it's got nothing to do with the medium voltage. It's very strong, as I showed to you the concept and the stations they put up in Germany. Most of them are not in a tree, but they are in a circle installation. So that means they back up each other quite tremendously. So there is a strong voltage there. But when they put it to the 1 second interval, you can see the red dots. So one of these inverters created a problem in phase 1, 2, or 3. And when they did that, you had these trouble of spikes going down. And that was enough that one of the other inverters picked up the noise in the AC grid and switched off. By doing so, all the other inverters triggered the same problem. And then 3-4 times a day, the whole system shut down or partially. Here you can see the same interval with the voltage difference, with the variations also in current. So it's interesting to see that small pickups, variations in the phases is enough at that time to cause troubles for these inverters. That's the picture after 2 days installed in some areas, not all of course, but you can see the condensing water from the nighttime, and you can see that you use some cleaning intervals to keep the modules clean. Of course, it's also in specific periods of times. That's the checkup, like I said, I do. It's a C-word, it's a multimeter, whatever you have. Check the voltage of the modules. In this case, it's 517. It's the 6.49 is the current. Is that similar to the current you expect during these times when you have a specific irradiance, 1,800, 600 watt per square meter, and then you can see the R-ISO. So the string is okay, it's 19 mega ohm. That means the problem is somewhere else. So if you measure that on top of the roof, on a free field installation, so that means the string, the table is fine. We have an earthing point, we have the specific, I mean, like I said, those were the old days with the modules, and it will show you still have 570s, not too much, but you still have that. So you expect to have these values at the AC side as well. So that means once you engage and put it back to the system, you want to have an MPPT of a similar thing. So if it's lower or if it's higher, you either have a mismatch or there's a problem with the other strings. So take the other strings down and see if this string, single line, will have the same irradiance, or you have, which I also have, I have two devices. It's one at the machine and one in the field. And I ask the people, what have you got? And then I check on my side. If it's the same, perfect. If it's not, you must think about another problem. So again, the inverter cannot see those values. If there's no interconnection from the inverter earthing towards the tables, towards the modules, towards the roof, he will not see 19 mega ohm. He will half it down. So that means then we are back at 600 kilo ohm or 800, and then he will not connect. Could be because of one string, could be one is missing, or some other issues. So think about this. Generator grounding is either the inverter or the transformer or the modules. So wherever you are, that's what's happening. So, and whenever you have a voltage difference between the modules, inverter, generator, or in this case a hybrid system, a battery bank, then you will engage a problem. Once the equipotential bonding is done, there is no voltage difference in between those systems, and the effect is less. The possibilities, like I said, in Germany, they are quite severe because we have so many transformer stations. In Italy, it's not, so that's why I choose this scenario. When we had the sun darkened, they switched off the whole system in 2015 for 24 hours. In Germany, during the solstice, they actually turned around, switched on some supplies, switched off some supplies. So they could manage very well the problematic behavior because this lasts only most of the time between half an hour and 1 hour. Like I said, you have different possibilities. That's a thermal check, and on top is the electric check. So you can use reverse current. So there are machines available where you, in actual fact, use the modules as a diode. I mean, at the end of the day, it's nothing else as an LED. So you reverse feed the current, and then you can see the behavior of the different strings in a thermal picture down on the bottom, in the EL picture at the top. So the dark wafers, they're already affected from PID. So the one side is mostly the negative. So that means the top section, most of the time, is affecting one side of the strings. So the plus always looks better than the minus. This is another sample where system have problems and don't have problems. So like I said, during the eclipse with the sun, that is now from 99 in UK. So you can see the drop of the UK power demand. Tuesday, Wednesday is the blue one is on Tuesday, and Wednesday when they checked between 11 and 11:30 the total darkness of the sun, you can see it went down quite dramatically, and you have this lagging. So the grid must cope with that. So there is some right-through technologies now available, also frequency-based systems. So they will put the system down and up again. I always use the sample from a VFD drive, similar to an inverter. So you can see here the AC drive and the motor frame, and when you have the transformer, so the green is always the amazing amount of stray currents from the motor and from the AC drive going back towards the transformer. So if the system grounding does not pick up, it could be that the motor gets faulty, has problems, and will have tremendous consequences. So this is another graph you should remember when you size the inverters and when it comes to the second grounding. So with the VFD drives, mostly it was 35 to 50 millimeter. So with an inverter, it could be 6 or 16 millimeter. That's fine. So just think about having, if you encounter problems, the first thing you should do is earth a second one, but you should done it in the first place already. So earth the chassis of the inverter if it's possible. And that's these huge parks, and you can see the streets. That's one system in UK, and they normally make a ring loop around all the tables, because the idea is step and touch voltage when you enter the field. That was a system I had to upgrade. You can see the DNO with the question marks has got no connection at all to the field. The bridges I've done in red or brown, it's around the transformers. So the before, you can see that the small lines from the arrays going down, there was no interconnection towards the inverter. So the inverter slept 1-2 hours longer, which is unnecessary. So it depends where the boxes of the DC combiners are done on site. So if you know the boxes in the field, it could be enough to earth those boxes, because there is the surge protectors inside, and you have these grounding and surge arresters and SPDs built into the cards of the monitoring or data logging system. So if they are spread in a nicely set up, not on the side of the module arrays, but in the middle, then you might not need to do this. Because from the inverter, in UK, for example, it would be armored cable most of the times. You can use the armor. And here you must use 6 to 16 millimeter cross feeders to each individual array. Or like I said, you have in this example, I did not know where the boxes are, so I asked the EPC where the boxes are. If it's not known, I would have done the thing like this. That's also this idea of a clean ground, or electronic equipment, or AC and DC are separated. It's wrong. So the power equipment grounding here, that's like your transformer. Then you have a lightning protection. In Germany, we make a mesh systems. It's easy. You don't have to think about anything. It's just every 20 meters there is somewhere in grounding. So if you've done it like this, goes down to a common electrode, there will be, for example, an earth pit, or the grounding of the transformer, or the grounding of an inverter. If you do the bottom, that each individual grounding, lightning protection, clean ground, water pipes nearby, those are all individual earth systems. That's not good, because then you actually manipulate the grounding on your own. Again, if you make a mesh system, you can overcome these problems. If not, you will face sometimes severe data logging problems and SPD searches I had in some installations. You can see here, for example, this is now built in one of the central grid inverters, burned out surge arresters, because the inverter grounding had nothing to do with the field. So whenever the field engaged backwards from the transformer or from the field, it burned out respectively either the SPDs in the DC side or on the AC side. You can see here the whole equipment burned down on the data logging side. So, and also the fuses on the left-hand side for the power box. So that is an issue. Sometimes DC cables, depending maybe they lie in parallel to the high voltage cables or medium voltage cables, or there's another source that sometimes is crossing your PV field. That's a problem. So that means you're picking up noise from other cables. I had cases before I energized the system. During commissioning, we had already between 600 and 3000 milliamps on an earthing ring. So although not used, not energized, no transformer running, a pump nearby with the water pipes running next to existing cables, inductively and capacitively engaged with a ring loop earthing, and that ring loop earthing had to be destroyed. So you make a meshed approach. So you earth individually inside the field via the DC boxes or via some other grounding, or like I showed you in the inverter picture, each individual string as quick as possible to the transformer. Why the transformer? Because it goes back where it belongs. The transformer is producing the energy and it will feed it backwards. So all the stray currents will eventually go back to the system. And because you have a lot of earthing grounds and a lot of different pillars going into the soil, the modules are always stronger than an earth pit. So that means sometimes they're hopping. So it's a water pipe, like I said, it has some resistance or maybe some isolating things inside. So that means it will jump over to the next earthing, will travel along till it jumps back to the water pipe. That could be hundreds of meters. That could be up to the point where the transformer or where the cable goes back to the transformer or wherever this is energized from. That was one of the remedies. Like I said, I made the voltage stronger, so I made a ring loop. So I used 2 phase 1s, 2 phase 3, 2 phase 2, bringing it back, upgrading the voltage. So we had a much stronger grid. So at the end, we were at 400. You have different, like I said, in America, different electric codes. They, like I said, like to use microinverters, rapid shutdown, and arc fault protection. Also low voltage next to the array, so they are below 30 volt. So this is one solutions they try to implement, and there you can see also the field after the fire. We had also some that's also known, some fires actually starting after it was de-energized. So in some Walmarts and in some malls, the system was actually put down because some intermatable connectors. Most of the problems, I would say 70%, are related to connectors. So that means the system, although it is de-energized maybe by AC or maybe by a stop switch, the DC was always on. So it's always 600 or 1000 volts on the roof, up to the point where it is going into the inverter. So although the AC is shut down, if the DC is not disconnected or the fuses are not taken off, there's a current running continuously, and it will, if you have a problem and if you use the earthing with a blind spot, have these consequences sometimes. Netherlands is since 2018, I think, very sought after in the PV systems, and they also have already capacity issues, so they have to upgrade some stations similar to Germany and interconnect even to other parts of countries. So that's just some capacity issues. There you can see the grounding practices again. So if you use shielded cables, and if you have these similar output like on a VFD with the inverters, you should use a specific grounding method to keep the ground as clean as possible. So it should always be quickly drawn backwards to the transformer. So it should not run over the water pipes or some other issues like it is on TNC networks. I had a case where the system was running for 4 years, Suntec modules and Sunny Mini Central 10 years ago. And there was a 30 kilowatt system added. So it was 300 kilowatt running with almost 1100 kilowatt hours per kilowatt peak, which is quite good in Germany. And all of a sudden, after 4 years, the modules degraded. So I was called out, and they wanted to replace half or 30% of the modules to see what's going on. And then I checked the inverters and I checked the leakage current, and I saw that the leakage current in the water pipes and the grounding was tremendously high. So then I checked the AC boxes on the system, and then I saw that it's a 5-core cable, but there was always a bridge done. So after they split off the neutral and the PE, which is in actual fact not even allowed, also not in America, they regrounded it. Sometimes they do it on purpose, like this guy, or sometimes it's not done on purpose, it was a mistake, and they did not know where the cable was going through. So this guy installed a 30 kilowatt system, checked the other system, saw that it's not bridged at the AC boards, so he made at 10 AC boards everywhere the bridge. So when I took off the bridge, then the system jump start again to the old values, because the stray currents was just from each individual inverter back to water pipes, back to the building, and it destroyed the MPPT capability of the inverter. And the inverter was, funny enough, secondly grounded. So I was thinking I'm on the wrong route and the modules are maybe really faulty, till I opened these AC boards. And then I saw made out of a TNS system, a TNC system. So with a 30 kilowatt system, he destroyed now still at 30 kilowatts, because he used only a 4-core cable. And he was not willing to run a separate wire. So, like I said, I changed the bridges and put a 50-meter long cable, 16 millimeter earth to the newly installed system, and then the system was running as day one. That's different devices. So you have inverters. This is again in America, where you have these rapid shutdown. So either it's one single unit or each individual, like Tiga, I think they use each individual modules to have one of these devices plugged in. There's no functionality sometimes, just that when the inverter or the AC has a blackout, they will shut down either each individual module or the whole string. That's string solutions people used. You can see how many areas of solar fields. This is just now with 5 symbolized. But they do like a snake connection. And that's actually the worst, because you infiltrate the temperature zones. You have lots of different earthing capabilities if it's not done correctly. So you should think about making horizontal lines. So that means from the left to the right, not in some areas it doesn't work, but then you should split them. And because you have at the bottom, like I showed in Dubai, you have 55 degrees on the corners of the roof, and then when you have a breeze, you have 40 degrees. So that's like 15 degrees differences. So those differences, the inverter has to match now. If you make temperature zone installations like I prefer, then you have always similar approaches, because it could be that the first module has got like 50 degrees and then it carries on the heat to the next and to the next. I saw roofs installed 10 or 15 strings, so the whole roof was covered with modules, no breathing, no walkways in between. So that changed already. But if you don't do it this way, you must imagine you have between 15 and 25 degree difference from string on the bottom to string on the top. So if you use, for example, all the strings on the top, the output would be all 75 degrees. And then you go to the bottom further on, that means you have individual strings with 50, 60, 70, and 75 degrees differences. If you couple it this way, you get a much better output, because those individual DC combiner boxes or these individual strings work much better with similar outputs. You can see it downstairs with the current. So for example, the one makes the current with 6.5, the other one with 7, the other one with 8. So if you have even multi-string inverters with different amount of currents, but the same voltage, of course, or similar voltage, then you have to check. If you take it off, that's the fine tuning I always say, put the 8 amps together, put the 6.5 together, put the 7 amps together, and then you will see you've got a much better output. The best, of course, would be if you have an inverter, all of the strings will be 6, 7 amps, and all of the strings will be 8 amps. You will also see the same if you, that's what I'm doing most of the time, if you have shaded strings, I put them all into one inverter. So that means I can oversize this inverter. If I have 12 strings and normally I only put 10 strings into the inverter, I just put 12 strings in, because I know these strings will not perform the same as a 10-string inverter or even 8-string inverter, because they are shaded. That means you make the 1.5 or 1.27 DC-AC ratio to overcome the problematic halfway 50 to 60% efficiency of some inverters. You will see otherwise always inverters running on 50, 60% load, while all the other inverters are on 100%. So this, like I said, this is another example, 2.8 gigawatts in UK, for example, during the quarterfinal against Brazil. So TV systems, championships, weddings, royal weddings especially, they will have some surges in the system, and also the PV systems, of course, and any other system have to cope with that, because all of a sudden you will have a high voltage. Grid codes, Europe, very different in the settings. Like I said, some people use the German grid settings in the beginning, and then they changed according to their local country law, because of course they know their grid much better than the other people. Italy had a self-sustaining grid, so it used to be something like 10 minutes till it goes over these cycles, and it checks everything, and you can see that this is now from 2012, but all of this remote P, trip, low voltage right through, high voltage right through, this was all engaged, while Germany was less optional or above some specific criteria. It changed again with a medium voltage supply. And this is just a sample how Europe, Spain, or different countries were dealing with different frequencies with the cosinus fee and stuff like this. As described, you will encounter some harmonics. I had one case now in Vietnam. They forgot to earth the transformer. It was visually earthed, but the cable was lying in the trunk, and it was not connected on the other end. So what happened was they had harmonics of 10 to 20% sometimes, and then off again, and differences in rainy and in sunny conditions. And once they measured the stray currents of the transformer and they didn't find one, then they changed it, and then they saw that actually the cable was not done. So after they did that, it went below 1%, and the magnitude is between third and 40th order. So it's actually quite high. Why? Because different inverter manufacturers have got between 10 and 25 kilohertz as an MPPT sample. So that means we are actually in a high frequency noise, and you can actually measure that.
Mr. Elio, if you go back to the previous slide, the graph are not clearly shown. Can you make it?
Oh, let me see.
The previous one. Oh, sorry.
Let me see.
Okay.
Checking.
Yeah. Sorry, I interrupt you. I thought it's easy.
Yeah, it's, I will check later again, and then okay. After the next break. 10 minutes past. Do you want to make a break or later on?
Yeah, it's better to have 5 minutes of break.
Okay, then I put it back.
Okay.
Yeah.
Yeah, dear guys, we finish our second hour of this training. We'll have like 5 minutes of break, and then we'll start our last hour of this webinar. So stay tuned, and we'll get back to you soon in 5 minutes. Thank you.